Okay, so let's continue our yesterday's lecture. So just a quick remark on the question. So even though Chomsky might have had different applications in mind when talking about grammars and languages, in our case, these grammars and languages and alphabets are very concrete mathematical objects. These are, even though we made analogies with natural languages, this is not a natural language and it's not a part of psychology or anything. We're just talking about mathematical sets, and everything we say is very precise and can be either proven or something else. So let's not go to proof theory as of yet, but our statements that we say are true are actually proven. So these are specific mathematical statements and not just some things that can turn out to be wrong or right or something. So in our case. So okay, so this is what we looked at yesterday in the end. So we said, so maybe look at it one more time. So this was, we had a hierarchy of, so the grammar was four things: non-terminals, terminals, production rules, and the start symbol. Start symbol was a non-terminal. Then we had some bunch of terminals, which these are my alphabet symbols that I had for my DFA would be like things that should go into terminals in this language. And so these are the strings that you're producing, and the production rules are the rules that you are, the productions are the rules that you're using to produce your strings, basically. So this is a general grammar. If you put on no restrictions on your grammar whatsoever, you call your grammar type 0. And the hierarchy comes from the fact that these are like included into each other. Type 0 is the most general one. Then type 1, CSG grammar or context-sensitive grammar, is the one where your production rule on the left side is shorter or equal to whatever is on the right side. This was type 1. Type 2 is type 1. That means the left side is shorter or equal to the right side, plus the left side is just one letter. This means you can also translate type 2, the context-free grammar, as left side is just a single non-terminal and right side is not empty. That's all you're requiring, because this is somehow redundant here. If you just know that size of u is 1, so it has to be bigger or equal to 1. This is basically what it says. And type 0, what we call regular grammars, or type 3, sorry, what we call regular grammars, is again a type 2 grammar, meaning you have just single non-terminal on the left-hand side, and all the production rules are like this. So single non-terminal implies terminal something, some non-terminal, or single non-terminal implies just a terminal letter. So only two types of production rules you have. So it's a very special case of a context-free grammar. The regular grammar is. And then I said it's going to go into your exercise that context-free grammars have derivation trees. And we actually saw the example of a derivation tree, blah, blah. And we saw that if your word can be, so the exercise is that if your word can be derived in your grammar, that means there exists a derivation tree. And vice versa, if you have a derivation tree, then your word can be derived in the grammar. So you can read your derivation from the tree. And then in the end we were here and we said that, okay, all these definitions of the grammars here ban you to have an empty string. Basically, all of them here require you that the right side is, let's say, other than the type 0 grammars, like this one here, requires you that this guy is longer or equal to the left side, and the left side cannot be empty by just the definition of the grammar. So u is not empty, so the size of u is at least 1. So if you require that v is bigger than equal to u, which is the left-hand side, then you're requiring v to have size at least 1. So you can never have a derivation that produces a epsilon in this case. However, we want that. We want that because as computer scientists, you are thinking about DFAs, NFAs, and your machines that compute things, and we want to think of grammars as machines also. So if the language is produced by a grammar or derived from the grammar, then you want a machine, some specific machine that creates this language, accepts this language. And so hence you want your epsilon somehow. So if in your, let's say in your DFA, your start state is also an accepting state, you have epsilon in your language because you're just starting with nothing and you're accepting it. So you want your grammars to create epsilons if you want to describe them by machines. And how we solve this in the last minutes of the previous talk is that you just add, maybe we write this. So you just, first we said that you have a start symbol S like this, and then you add this rule. What? This disappeared. So you add this rule like this, that your start symbol creates epsilon, but if you do this, if your start symbol is on the right-hand side of some production rule, maybe you have something like this, I don't know, some production rule like this, then this will allow you to produce epsilon by just substituting this twice, and then A will produce epsilon, which you might not want, because you're also changing grammar by adding this. So in order to remedy, we said that, okay, we create a new start state S prime, we create a new rule that your new start state takes you to the old start state, and then we just add one more rule like this. And in our definitions of grammars, we just add, this is true, there's just one other than, so we give it an exception. The exception is this rule. Start state can imply epsilon. So we just add this there and that's it. So we have a start state which never occurs on the right, and we add this new rule that you can do this. And now nothing changes, you just add this one rule and you're now good to go. So here is what we did. And now let's look at, now we're ready to prove some things. So the first thing we're going to prove, we're going to look at the regular grammars here. And let's look at, so many things. Let's look here, let's first skip this, and let's look at our regular grammar. So the regular grammar, so grammar is something what? So you have non-terminals, terminals, production rules, and start symbol. I have to tell you what they are to give you a grammar, but anyways, let's say. And we say that this grammar is regular if all my production rules, so if this is a production rule, so if this is my rule in P, then U is just a single non-terminal, and I have only two types of rules basically. So I have U implies, let's recall which side are we talking about. Oops, where was this? Full screen here. So AB. So sometimes there's a convention here which side you put a terminal on. AB and A. So it's like this, AB or U implies. So these are the only two rules that you have. So this is a definition of a regular grammar. I want to prove that this is exactly, if your grammar is regular, the strings that you're producing is exactly what DFA accepts. So I proved that DFA is exactly the same as regular languages, by definition of the regular languages being defined by union, concatenation, and the Kleene star operation. But now I'm using grammars to define the same thing. And then I'm going to move up the Chomsky hierarchy and create machines for all types of grammars I have. Like the regular grammar will have DFA. Then the context-free grammars, we will have the push-down automata. Then context-sensitive grammars, we will have some kind of Turing machine. And then type 0, so with no restrictions. So anything that can be actually computable strings, so to speak, will be Turing machines. And then we will somehow state the Church thesis, which is thesis in computer science, which is the most, so we will state that everything that can be computable is computed by a Turing machine. So every computer you can even imagine or have will be a Turing machine, just very complicated one. But anyway, so let's get back to here. So I have only two rules of this form. And now I want to say, let's say I have regular grammar G, so it's a regular. And let's say I derived a word A2, A3, up to, I don't know, AN. So some N symbols I derived, right? So these are like N different symbols. This is the string I derived in this grammar. Whatever my terminals are, whatever my non-terminals are, let's say I derived this. I want to ask you, regular grammar now is also a context-free grammar. It's a context-free grammar which has even more requirements. So it has a derivation tree. So how will this derivation tree look like? Just deriving a very general string like this. So it will start with the start state. So this will be your root. So what can happen here? This is what I'm asking. What can happen downstairs? Yeah, so there's only two possibilities. It's either this or this. If it's the second one, then I derive A and I'm finished somehow. Then I just derive one symbol. But I want to derive n symbols, so I'm only left with using this guy here. This guy. So it has to be something like this. It has to be A1, I call this guy. And then let's call this guy B1, whatever this guy is. Right? This is the only possibility. Okay, well, now what else? How can this go on? The only possibility I can do this is now that this derives A2 and maybe like B2. And then this will derive A3 and maybe like B3. The writing is horrible, whatever. And this is the only way this tree can look like. Then this continues and it hits, I don't know, Bn somewhere, and it has to end there. So maybe then at the end I use this guy in the end, and it's like An. So this is what the tree looks like. And then this tree, the leaves are A1, A2, A3, An, and they exactly derive this thing. So this was completely general. Do you all agree that this tree has to look like this if it's a regular grammar? So every regular grammar, every derivation tree in my regular grammar exactly looks like this. There is no other way. This is completely general. A1, An can be anything, maybe zeros, ones, whatever, X, Y. And B1 to up to Bn can be anything. Maybe they coincide some places. But this is a completely general derivation of completely general string of length n. But this is the only possibility of a derivation tree in my regular grammar. And the idea is that this is basically a DFA. It's like a different way of writing it. You're starting somewhere and you're like hopping in from state to state, from S to B1, and you're kind of reading A1. So you start at your start state, you read A1 and you go to B1. You read A2, you go to B2. And then in the end, you have to add some accepting state, and you accept if there is this path. So this is why this is just intuitively explanation of why these things work. But let's go back to our slides, which were here. So what I'm trying to prove now, this is the lemma that I did not state it out, is that if L is generated by a regular grammar, then it's accepted by NFA. So let's say NFA. We know that NFA and DFAs are the same. So NFAs will be easier because you might have a rule that B1 produces A1, but B1 also produces A2. You can have that. So we want NFAs. So this drawing here is exactly what we draw, but upside down. And maybe indices are up to n-1 and n and b1 whatever. Maybe I made a mistake in indices, I don't know. So it's the same tree, and the statement is that the derivation tree from A1 to AA in a regular grammar always looks like this, which we already convinced ourselves that this is the case. And now I'm constructing a DFA from this picture, basically. So my states will be everything, so all non-terminals, so B1, B2, B3, this will S, B1, B2, B3, will all be my states, plus I will just add one more state, so I finish. So I know that I'm finished. This will be A, my accepting state. My start state will be S. So if I want to replicate this, basically, I start with S like this. This will be my start state. So I'm going to draw a DFA from this diagram now. And my accepting states is either my A that I added in the end, or maybe S is also accepting if I want my language to have epsilon. Now, if I have this special rule that I added, this guy, if it's there, then I also make my start state accepting, and that's it. But let's say this guy is not here for simplicity, and let's say this guy's, we don't have this rule, and then we just look at that accepting state is A. But now the transition functions. So how do I transition? So what is delta NA, meaning that when can I transition from non-terminal N when I read A? When can I transition to B? This only happens if there is a production rule NAB. So in this case, there is a production rule that here, on the left-hand drawing, there's a production that S produces A1, B1, right? There is this production rule, otherwise I wouldn't be able to draw this. So there is this production rule like this. So that means, well, here. This means that there is here my definition, this is what my definition says, that from S, I can go to this guy here. So basically, let me not confuse you. If I read A1, I can go to B1. This is what it says. However, this is an NFA that it might be possible that this thing also happens. I don't know, some P tilde. If I also have this rule, I also have to have this thing here, because in my derivation tree, I used the first guy. I used the first production rule. However, I could have used the second production rule if I wanted to produce something else. So even though I have many possibilities to produce, I also have to include it in my NFA. So that's why this is an NFA. But let's just continue. So let's just ignore this for a moment and just continue replicating this guy. Then from B1, after reading A2, I can go to B2. And then you understand the gist. It goes on like this. And in the end, I read AN and I go to BN. Let me check. Where do I go to an accepting state? Oh yeah. So no. See, sorry, this is not correct. So in the end, I have this production rule in my grammar, right? As it's written here. This is my production rule. There is nothing here anymore. So this is if I have this production rule, then I have to go to an accepting state. This is basically what it says. So somehow I continue this, I read AN, and I go to my BN, which is an accepting state. So what am I doing? So I go here, I read BN minus 1, and after I read my last guy, which is AN here, I go to an accepting state. So my pointer is gone, unfortunately. Cannot get it back. Anyways, so I introduce these transition functions. From B1, you can go to B2 reading A2. If I have a rule like this, so the rule here is in my grammar, I have B1, A2, B2. This is the rule I had in my grammar, so I produce this transition. But if I have this rule like this, for example, Bn gives you a n like this, if this is the only two possibilities of rules I have, then I produce this transition that goes to an accepting function. That's it. Basically, as I said, you have this tree, and I transform this tree into a NFA. So every time you can draw a tree, and we proved in our exercise that if you can draw the tree, you can derive it in a grammar. This just says that if you can derive it in your grammar, you can build an NFA that accepts it. And it turns out you can do it vice versa. So here it is. Here is the proof. Basically what I said, the proof proven that if you have a computation like this, so if you start with a word in your grammar, I have no pointer, so if you start with your word in the grammar, there will exist a computation in your NFA that goes to an accepting state. This is how I drew it. So your word will also be accepted by NFA. And the other way around. And somehow the next lemma that we want to prove, so the other way around, let me just state it out. So if your word is accepted by your machine, then there's an accepting computation of M with input W and states there. So it's an accepting computation. There's some states have to happen, S, B1, Bn minus 1a. Then exactly you draw figure 2 on the left. So you draw this figure here, and then this figure will be a derivation tree. So if you have an accepting computation, you draw a derivation tree. If you have a derivation tree, you draw an accepting computation. This is basically what it is. So this proved that if language is generated by regular grammar, then you can construct an NFA. But you can do it vice versa also. If you have an NFA, let's take DFA in this case, because NFAs and DFAs are the same. Sometimes I use DFA when it's convenient. So here lemma 4 says that if I have a DFA, so I have states, I have an alphabet, which I now denote by T, because I want my alphabet to be used as non-terminals. So if I have my DFA, and it accepts some language L, then there I can construct a grammar that generates the same language, and that grammar will exactly be regular. How do I do this? This is basically an exercise. What happened? Yeah, here. So how do I construct a grammar? I do the opposite. So if I have a transition function that takes from B after reading A, if I have this in my DFA, then I could create a production like this. And if I have from B, let's say from state B, when I read go, I go to state C, and if my C is accepting, then I create this production. That's it. So I look at my DFA. For all transition functions, I add this production rules, and for all transitions that go to an accepting state, I add this production. And then it's very easy exercise to prove that the grammar you get is exactly the one that is accepted by this DFA. Just pay attention that the terminals that you take for your grammar should be exactly the alphabet of your DFA. So if your DFA runs on strings 0s and 1s, your terminals should be 0s and 1s. And your no-terminals are just the names of states. That's it. So we just simply prove by derivation trees, you prove that DFAs basic, so regular languages is the same, are the ones that are generated by regular grammars, and these are the ones that are accepted by DFAs. So we have this trichotomy, so to speak, so regular languages, regular grammars, and the machines that accept them. So our next aim is to actually create something that accepts context-free grammars. I mentioned this a couple times already. Have you seen this? So for regular grammars, this is circled here already. So this is DFAs, which is, by the way, same as NFAs. So DFAs and NFAs are the ones that accept things generated by regular grammars. So here, the machine is called the push-down automaton. How many of you have seen the push-down automaton? So where? Here or somewhere else? So maybe in OSA. So the push-down automatons will be discussed next. But now my question is so recall what we did with pumping lemma, right? With pumping lemma, we proved that there exists a language that is not regular. We specifically gave an example of this language. What happens here? What the hell? So this language here was not regular. So n was whatever. N is natural numbers with 0 maybe. Doesn't really matter. So we know the language that is not regular. Okay, but we know that this language is also context-free. Why? Because what's this? Yeah, here in this red square, we see that this language is generated by this grammar, which is a context-free grammar, basically by definition, it satisfies the requirements of context-free grammars that the right-hand side is longer than the left-hand side, whatever. So it's a context-free grammar. And so this language is a context-free language because it's generated by a context-free grammar. So now my question is, does there exist a language that is not context-free? How do we know this? Okay, we know that some languages are not regular. We enlarged it, we got a language that is not regular, but we know it's context-free. How do I know there is anything beyond context-free languages? Maybe every grammar I come up with can be rewritten so that it's like this. So that it's context-free and it generates the same language. How do I know that something exists that is not context-free? And this is where the next lemma comes. So maybe we do this today and we finish. Here is what we have. So it's a bottom stage of hierarchy, meaning the lowest hierarchy is regular languages, and we know that there exists a context-free language N, which is not regular, and we know it's context-free. So now we have a pumping lemma for context-free languages. So there is a pumping lemma similar to, like the pumping lemma yesterday, we had that if you have a language which is regular, you can decompose it in 3 parts and you can pump in the middle. So now there is a pumping lemma for context-free languages also, which will help us prove that there exist languages which are not context-free. That means that are not even accepted by pushdown automata or whatever we're going to construct. So for every context-free grammar G, there is a constant number n0 such that now it just starts the same way as for regulars. However, I just use context-free grammar then instead of regular language. So for every context-free grammar G, there is a number n0 such that if you take again a word that is generated by your grammar, the same exact phrasing as we had for before, and your word is longer than n0, this is supposed to be big W. So if this word is longer than n0, it can be decomposed now in 5 parts. Before it used to be 3 parts for regulars, so now it's 5 parts. Let's call it big W equals u, v, small w, x, y. Such that v and x are not epsilon, whatever, and v, w, x is less than. These are just technical assumptions. So these are technical assumptions. So technical things that you might find it very useful when you want to prove something. Especially, well, this part is not really technical. This part says that if I do not impose this, this will be trivially true. Think about it later, but okay, where can I, so I have decomposition like this. U, V, W, X, Y. So this is my word now. It decomposes into 5 parts. And what I'm saying is I can raise V and X to any power I like. It will also be generated by the grammar. So for example, if this W is in LG, this is in LG, then I'm claiming that U, W, Y is also in LG. That means if I take I equals 0. I'm claiming that U, V, 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 W, X, 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 Y is also in LG, and so on. So I can multiply as much as I want V's and as much as I want X's, and I will still stay in my grammar. This is the famous pumping lemma for context-free language. By the way, you can find all this, all the pumping lemmas and the proofs in Michael Sipser's books, also in Hopcroft and Ullmann, but the MIT textbook that we're also using is by Michael Sipser, and he has intuitive explanations and everything, so you can find it there. Michael Sipser's book and the standard Bibles for the subject, which is Hopcroft and Ullmann from the 60s, you can find it there too. Okay, how do we prove this? So let me give you an intuition first. So we're dealing with context-free grammars, right? So where was this? Here. So our G, so let's see how much time have I? Yeah, we can prove this. So let's say G is my context-free grammar. And let's say I'm derived and I know that my word is in L of G. This is the premise of my lemma, right? So my word is in L of G and my G is my grammar. Now, if this is a context-free grammar, so let's write it down. Context-free grammar. W has a derivation tree. This is the whole point. Let me draw the complete general derivation tree. This is a tree. It has a start state here, and here are my leaves, and this is W. Maybe make it nice. Like these are my leaves here. I drew it this way. These leaves might be like this, but whatever. And this is my start state. So you all agree that this tree exists, right? So what are the inner nodes here? So this is my question. There are some nodes in this tree sitting inside, right? So inner nodes. So inner nodes are my non-terminals, right? Leaves are my terminals, but the inner nodes can only be non-terminals. So these are like non-terminal 1, non-terminal 2, maybe like this, non-terminal 3, like this, right? So this might have much more things coming out. So what I'm claiming is if W is very long, the first claim is, without any mathematics, if W is very long, then my tree is very tall. Because you have to do more things to derive longer words. So your derivation tree has to be taller and taller and taller, the bigger your word is. So if W is very long, S is very tall. Well, not S. The tree is very tall. The tree is very tall. Let me erase this so we can see it. So if tree is very tall, there are too many inner nodes somehow. The taller the tree, so let's say this tree is very tall, so the height of the tree, this is H, is very long. So all the nodes here have to be non-terminals, right? So all the nodes are non-terminals and this H is very long, let's say. The height of the tree is, you know the height of the tree is the shortest distance from the leaf to the start, right? If the tree is very tall, the height H is large. H is large. So if H is too large, I will run out of terminals. So again, by pigeonhole argument, some non-terminal, I think it's called R in your book, so let's call it R, has to repeat. Just by intuition, if the H is too long, that means W is too large, then on the road of my height, one of the non-terminals has to repeat because number of non-terminals is finite. So at some point, when you're growing your tree bigger and bigger, this thing has to repeat. So let's look. Let's come back to our PowerPoint and look at the statement of my lemma here. ხო მაგას ახლა ზუსტად დავამტკიცებ რა რიცხვები უნდა იყოს მან, მაგრამ ჯერ ინტუიციურად გადიდებას ვეღარ პოულობ. Okay, I can't find the magnifying glass, but you still can see, right? The assumption is this, that if you have a context-free grammar G, there exists a number such that if your words are longer than these numbers, so number. So there's a fixed number, I will tell you what this number is, maybe 9,344,000, that if your word is longer than this, my argument will go, if my word is longer than this number, it has to be taller than some number, and that some number, I will choose my width of my W so that this number, the height, will be bigger than the amount of non-terminals. So I will choose my N0 in such a way that if my words are bigger than N0, then the height is larger than the number of terminals. And if my height is larger than the number of terminals, then one of the terminals has to repeat. ხო, ისე ავიღებ და აი ამ რიცხვს n-ს ისე შევარჩევ, რომ მაგხელა სიტყვა რომ გამოვიყვანო, h-ი n-ზე მეტი უნდა მქონდეს უეჭველი. I will do this in a minute, exactly give you the numbers, but just for intuitively speaking, then this one thing has to repeat, and then we look at your picture from the book. So this is your tree from your book, and you can see that some R repeats. So let's say this R repeats twice on the road. Then let's look at so it repeats, so there's two R's. One of them is higher than the other one, right? So one is higher, one is lower. And I call whatever the lower R, if you look at the tree that is rooted at the lower R, it derives something. I call this guy X, whatever the lower R derives. And whatever the higher R derives, I call dxy. Because it also derives X. So if R sits here and then the other R sits here, this guy derives something, I call it, but this guy also derives something which is actually includes X. So I call this guy V, I call this guy Y. The string that it derives will include X because it's higher. And what I can do now, let me erase this so you can see. So you see on the picture, I can remove this R from your tree. So basically, let's take blue. I can remove this guy from your tree. So you can see what happens. So instead of drawing in this horrible way, you can look at the drawing. You can take the top R and glue it to the bottom R. So whatever the derivations are used here, the same exact derivations can also be used here. So the fact that the top R is deriving some things, it's also, so if you don't think of a tree, but maybe think of the derivation. The tree is the same as the derivation, right? The first R, the top R, is the first thing you see during the derivation. And the bottom R is the one that you see afterwards. Whatever this guy derives also includes whatever the next guy derives. So top R will derive, after many steps, Vxy, a string that contains something, then X something. Because it goes maybe like this, blah, 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 then R again, blah, 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 and this part, then this guy derives X. That means in this longer computation, I will have X if I use it on R, and I will have some other things to the left and to the right. This is what basically this thing is claiming here. That you have top R, bottom R. Whatever bottom R derives is called X. And this is also has to sit inside whatever top R derives, which is V and Y. So I call these things V and Y. This is my decomposition. And what I'm claiming is now that in my tree, I can take the top R and glue it again to the bottom R, and I will get U, V, V, X, Y, Y, Z. როგორ მივაწებო? ტერას მივაწებო. ტე თუ მეორდება კიდე შემილია კი. იმიტომ რომ ნახე მეორე, so you have R and then some production, right? And then something, and then R again. So it's basically like this. Some V, R, Y. This is what I'm claiming. Whatever V and Y is. Let's not call it V and Y because at this point it also might include non-terminal. So let's call it F and G. So this is what I'm claiming. Now, the production rules that I use, maybe the other one, the production rules that I used here in these red dots to produce some other things here can also be used exactly here because it's the same R. So let me pause it and explain it. So maybe it's actually better to see on an example what it looks like. So maybe our example is gone, but anyway. So if you have a tree like this, and let's say you start with start symbol and tree like this, like this, like this, and let's say I used R here as my non-terminal, and then again I used R here. Why can I just remove this? So that means that all the production rules that I used after R could have also been used up here. And it will produce something else. This is exactly what I'm doing, basically. I keep forgetting that my picture is here. So you can take all the production rules you used after bottom R and use them at the top R. And then what you will get is this. Because the bottom R produced X, the top R will also produce X. So you will remove V and Y. And you can do it the other way around. You can use the top R in the bottom and then you're pumping on V's. You can do it as many times as you like. You keep pumping and pumping. ერთი და იგივე non-terminalია. Ზუსტად იგივე ტიპია, მეორდება. So it's the same non-terminal. So all the production rules that ხოდა მაგის გარანტიას ახლა გავაჩენ. So let me give you the guarantee that this will happen, that one is under the other. So let me give you this guarantee now. Let's say I have a derivation tree. So that means I have a grammar that is NTPS, and P just is some rules, right? Like this. Dot. I don't know what's used in your slides. I think S. Let S small. Let's use something else. Let's say B will be the length of. So maybe if I say this mathematically, it's the maximum of what? Size of V such that UV is a production. So what is this? This is the longest possible string that is produced in your production rules. So B is a number. So you have finite amount of productions, right? So first production has 500 on the right hand side, let's say 500 length string. The second production has 234. The third production is just S empty, whatever. There is a number which is the longest possible production rule that is written on the right hand side, like this. You agree, right? So if you give me productions, there is the longest one. The longest string that is written on the right. So let's say this number is B. Now I'm asking you a question. Let's say I start at the start states. How many sons can this guy have? At most, how many sons can this guy have? So let me start this. So I start with S. არა, ერთ ნაბიჯში გეკითხებით. No. So look. On the first state, so I start with my start state and I'm building my derivation tree. ხო, პირველივეზე მაქსიმუმ რამდენი შეიძლება ქონდეს შვილი? I'm just making one step. It might even not be. Some of them might be non-terminal, some of them might be terminal, some of them might be B's, X's. Okay, how am I? So yeah, this is the problem. How am I writing this? When I'm allowed to write something like this, that S has sons in a context-free grammar? So I have to have a production rule like this. only then can I write this, right? I'm writing a thing if I have a production rule. So now I'm asking again, only then can I write the derivation, start to write the derivation tree, if I have a production rule corresponding to that son inheritance thing or whatever. So now I'm asking again, at the most, how many sons can S have? Oh. B. Oh, that's classic. It can be B because what is B? B is I just wrote down all possible productions, whatever my productions are. I wrote down all my possible productions and I took the longest one that can be on the right and I called this B. It's a finite number. Maybe it's a very long production, but none of this can have at most B sons on level 1 because if I use the longest production I will have B sons, but every other will have less. Okay, now question 2. How many leaves can I have in level 2? Huh? So on level 1, I can have at most B children. What about on level 2? P quadrati da rato. So look, you start with a start state. Here you can have at most, huh? ხო, ყველაზე უარეს შემთხვევაში. ყველა არის ბ-ზე ნაკლები. In the worst case scenario, you will use the same thing again. So at most this guy can have B. Everything else you use will have less than B numbers. So level 2 will have B squared. What about level 3? It will be B cubed. So now what I'm asking you, so on level 3 will be B cubed, B4, B5. What I'm asking you is now, let's say I have a derivation tree of height h. What is the maximum size of thing that this can derive? Yeah, B to the power h. So the tree of height h can derive at most B to the power h size word. There is no other possibility if B is the longest possible production, right-hand side of the longest possible production. Now I'm asking you, let's say my word is of the size what time is it though? We ran out of time. So the idea is that if I know the size of the word, let's say, can I talk about what is the least amount of height that the tree has to be? So reverse this question. So let's say I know the size of the tree, which is, let's continue this last time. We couldn't finish this, that's okay.